I bet you've heard all about the weird consequences of special relativity, like nothing can go faster than light, and time slows and objects get contracted when they travel very fast. What do these mean exactly, and why are they true? For instance, why is it that nothing can go faster than light? It does seem possible in principle. Say we have a rocket with an unlimited amount of fuel. If we fire a burst of fuel, the rocket gains some speed. With every additional burst of fuel, it gets faster and faster. This suggests that it could, in principle, keep getting faster forever. There does not appear to be any speed limit. It can go as fast as it darn well pleases. So why should there be a limit at all? Yes, the idea of a cosmic speed limit has been well established since the beginning of the 20th century, but you should be skeptical. This directly contradicts with our reasoning about how the world seems to work. We are going to need some solid evidence to back up these claims and why they are true. And trust me, the facts are stranger than fiction. It turns out that these facts about the way the world works can be derived from the result of an experiment, the Michelson-Morley experiment. This was considered by many to be a failure, but what a great failure it was. Though, before we get to the experiment, we need to understand the motivation behind it. Why was it done, and what would it explain? There are two ideas we need to cover here. The first is an idea about velocities, and the second is about light. Let's begin with velocities. You see, back in the old days before Einstein's theories of relativity, there was another form of relativity, part of which was explained in a previous video. Take a look at it if you are not yet familiar with inertial frames of reference, as we'll be building on those ideas in this video. At this point, you should know that no matter what speed you are going, you cannot do any experiment that could tell you that you are moving. Now, what does this have to do with relativity? The story of you, your friend, and the bus continues from last time. You both learned so much from your last experiments that you now uncontrollably crave for more science! You both design another experiment. You are on a moving bus and your friend is on the ground once again. You throw a ball toward the front of the bus and time how long it takes before the ball hits the windshield. The bus driver won't mind. If you take the distance the ball traveled and the time it traveled, you can calculate how fast you threw the ball. Let's say that the ball took 1 second to travel the 9 meters between you and the windshield. The ball traveled at 9 meters per second. Now, let's look at this from your friend's perspective. He sees you, the bus, and your entire experiment moving in one direction. Let's say that the bus is moving at 21 meters per second along the ground. Your friend can calculate the ball speed too, measuring the 1 second time interval and the distance the ball traveled. There's one difference though. The bus windshield is moving forward as the ball flies towards it. The ball needs to catch up to that windshield if it wants to make it there in 1 second. Taking this into account, your friend will calculate that the ball traveled at 30 meters per second. It's like the ball got a speed boost from the bus's motion, because you were already moving when you threw the ball. According to your friend at least. This is Galilean relativity. As you and your friend watch the same ball traveling toward the front of the bus, you measure different speeds. Just as observers in different inertial frames will disagree on who is standing still, no one can agree on how fast objects move. Asserting that the ball was moving at 30 meters per second is meaningless. All you can say is, the ball was moving at 30 meters per second relative to the ground. Or, the ball was moving at 9 meters per second relative to the bus. Now that we understand this idea, we can switch over to the second one. Light. Back in the 1860s, James Clerk Maxwell came out with what are known as Maxwell's equations, describing electromagnetism. From those equations popped out a special quantity, 299,792,458 meters per second, normally rounded to 300 million meters per second. This is the speed of light. This number is so important, but takes so long to write down, that physicists often just write a lowercase c. The conclusion is that light travels at c. Do you see the problem? We just learned that saying this goes at this speed is meaningless. This must go at this speed relative to something. The answer to this problem? Physicists explained it like this. Light is a wave, as was believed at the time. A wave needs a medium to propagate through. You cannot have water waves without the surface of water, and you cannot have sound waves without the air, or walls, or something. Likewise, you cannot have light without... We need a name for this. Let's call it the luminiferous ether. Fancy. A little too fancy, so let's just call it the ether. Light travels at 300 million meters per second relative to this ether stuff. This was also used to explain how light is able to travel from the sun and other stars to the Earth through what would otherwise be empty space. The ether fills that empty space so light can wave along it. As the story goes, If you are at rest relative to the ether, you will measure the speed of light as 300 million meters per second, c. But if you are moving relative to the ether, you will see the light traveling at a different speed. But this eliminates the idea that you can't do any experiment to prove you are moving. We have just found an experiment that apparently could tell you about your motion through the ether. So, which is right? The idea of absolutely standing still doesn't exist? Or light travels at c through the ether? Here is an idea that has so far never been disproven, and here comes along another idea that says it's wrong. Even so, most physicists believe that Galilean relativity had to be wrong, and favored the predictions about the behavior of light. But this is science. We cannot assert any claims as true until we have enough experimental evidence to be confident that they are. Which experiment will solve this conundrum? Ladies and gentlemen, the Michelson-Morley experiment. Finally! In 1887, Albert Michelson and Edward Morley collaborated on a super precise setup. It was what is called an interferometer. The actual experiment was more complicated than explained here, but it relies on the same ideas. A beam of light is shot toward a semi-transparent mirror at a 45-degree angle. The beam splits in two, each of whom bounces off another mirror and returns to the angled mirror, where some parts of the beam rejoin and hit a detector. If the split beams arrived at the same time, we would see a bright spot, because the beams were in phase. If the beams arrived at slightly different times, there would be a dark spot, a result of the beams canceling each other out, being out of phase. Now if this experiment were done on the Earth, at some point, the experimental setup will be moving through the ether, as Earth is always changing its direction as it moves around the Sun throughout the year. So, as the entire experiment moves through the ether in this way, one beam of light would need to travel a longer distance to catch up to the mirror moving away from it, similar to how the ball struggled to catch up to the moving windshield. But unlike the ball, light cannot get a speed boost from the moving light source. Light must travel at c relative to the ether, remember? So, the light beam must take more time to travel to this mirror, because it had to travel a longer distance through the ether to get to it. As a result, the beams would arrive out of phase and there would be a dark spot. If we rotated the entire experiment this way, it is at a unique angle so that the beams of light trace up the same distance through the ether, and arrive at the detector at the same time, in phase. If all these expectations were true, we should be able to rotate the experiment and see bright spots at some angles and dark spots at other angles. This would prove that the ether really exists, and you really can detect if you are standing still or not. Well, the experiment was done. The results? No matter how it was varied, rotating the experiment did not significantly change what happened on the detector at all. The experiment had failed to detect the ether. But maybe the experiment was not a failure. Let's see what happens if we just run with what the experiment suggests. It seems to say that light does not travel at c through the ether. The experiment can be moving at any speed, and the light will still look like it is traveling at c relative to the experiment itself. So, the conclusion is, everyone in every frame of reference measures light to be c. This seems like another problem though. According to Galilean relativity, speeds aren't absolute. Speeds are supposed to be able to be adjusted, depending on who is doing the measurement, like how the speed of the ball was different for you and your friend. But now, it looks like light is traveling at c regardless of how fast you are moving? To see what I mean, consider you, your friend, and the bus again. Now, instead of throwing a ball, you flash a burst of light while standing in the middle of the bus. So, according to you, the light burst hits the front and back of the bus at the same time. Now for your friend. According to the Michelson-Morley experiment, your friend should also see the light burst traveling at c, so he would measure the light hitting the back of the bus first, and then the front afterward. Wait, so according to you, the light hits both back and front of the bus at the same time. But your friend says that that same light burst hit the front and back of the bus at different times? If you've been following along this hideously long journey we are taking, your reaction at this point should be, what? How is this even possible? Light, you are a troll. What is going on here?